Oh, it's on, there's no assignment for it because it's optional, but it's under week 15. So the PDF and then the catalog. Yeah. Mhm. Right.
I don't think I.
Oh yeah, go for it.
Oh, just
Yeah.
kidding.
Okay.
Oh, that's a question.
Yeah.
You remember my helping notes?
Yeah.
If I test three materials, then my boundary conditions have to be the same, right? Because change
oh,
if
yeah.
my stress is different,
Yeah.
I can't compare it.
Right.
Is it okay for you?
Okay, so that can be two, so overall you need three, there's three scenarios that you
Yeah.
do, right? So you test three materials, all with the same boundary conditions, that can be two for those scenarios. I do want another loading scenario, like you change the boundary condition, but you can do that for just one of these two.
And for my conclusion, how would I do that? Because the result would be different.
Yeah.
I can't compare these three materials with each other.
Yeah, how about this? So how about you do three materials, and
Okay.
you do two different boundary conditions, two different loadings. You have 6 simulations overall.
Okay.
And then you can talk about that in. That's fine. Yeah.
So I have three materials.
Yeah.
Can you repeat that again?
Yeah. So for each of the three materials, you're going to run two simulators for them. One with kind of the basic loading, the other with the other, like, for all three materials.
So I have. Yeah. Right here.
It should be something.
I have like that. Maybe if I show you my scenarios. Okay, so
Yeah. So this is what I mean. So he has two different loading scenarios. So for each of these, the loads are going to be different. And so you can test both of these scenarios for all three of your materials. Does that make sense?
the first scenario is only the weight of the person and the equipment, and the second scenario is the impact force and the acceleration force and something else.
Exactly. Yeah.
Okay. So I have two scenarios for each material.
Exactly. Yeah.
And that's fine.
That's fine. Yep. It doesn't have to be just three. You can have more. You can have more. But the minimum. But I think for your case, since you want to test all three materials,
Yeah.
let's do two loadings for each material. So six overall.
Okay.
Perfect. Thank you.
Yeah. Yep.
I haven't really gotten around to coming up with ideas for the final
Mhm.
project. I was really asking, what's the date? Really have to be.
I mean, it should have a little bit more geometric complexity than the midterm project,
Mhm.
but not that much.
So let's say I wanted to just like this, like a video class.
Yep,
I just
that works.
do like the FAE on it.
Yep.
Then I'll just choose like different material, different courses on it.
Yep.
Okay. There anything else I need to add to it?
Well, the main thing is we need to find a CAD model.
Oh, okay, I'll come up with that myself.
Yeah, you either come up with it yourself, find it online, or just obtain it next month.
Okay. Great, awesome. Thank you.
Yeah. Yeah.
It's okay to just change the angle of my post.
Sure, yeah,
That's a new scenario.
that's a new scenario, because that's gonna change how the stresses are distributed.
Should I take like a course that's with an angle or just chain like 180 degrees, like
It should, I would do kind of off center.
Okay,
Like for
so
you,
something with an angle.
exactly, yeah.
Okay, perfect. Thank you.
All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, hanging in there, so. All right, it's final week, or one before the final, next week's the final week. Okay, so today's gonna be a pretty chill day, so we have I have an ANSYS activity for you. This is an optional activity, so you're not turning anything in for this. This is only just, if you were interested in using it for your final project, okay? And so it's basically, we're going off of what we talked about on Tuesday, which was all about kind of resonance frequencies, modal analysis, vibration analysis. And so we're gonna learn how to do this within ANSYS itself, okay? It's a very fast activity. I think it's only gonna take us maybe 30, 40 minutes. And then everything after that is just gonna be basically just project workshop, okay? And just like I mentioned on Tuesday, so the plan for the lectures for next week, I'm still gonna come here. I'm still gonna be here in lectures, both on Tuesday and Thursday. But I don't have anything planned. And so the idea with the lectures next week is to give you guys a chance to work on your final projects, ask questions about it in terms of, are you setting things up correctly, or maybe you're running into some issues with ANSYS. You want to run some things by me just to make sure things are good. Think of the lecture times next week as kind of extended office hours. Okay. And we're going to have some of that today as well. Okay. Okay, so if you want to follow along with the activity, obviously there's no assignment for it on Canvas because you're not turning anything in. And so if you want to follow along with the activity today, you're going to go to the week 15 page on the Canvas site. You're going to download the PDF, and so the PDF for the activity is EGME 410 ANSYS activity 6.pdf. And you're going to need the CAD file as well. So we're going to be doing this on a Gearbox. So make sure you download that one as well, which I need to do. Okay. Okay, any questions on this before we get started with the activity today? Okay, all right, so let's go and get started. Okay, so like I mentioned, the whole purpose of the activity today is to learn how to use the modal analysis tool within ANSYS. Okay, so what the modal analysis tool will allow you to do is that it's going to allow you to basically compute the natural frequencies of a part. So that can be really helpful because, for a part with any kind of geometric complexity, it's oftentimes very difficult to determine what the natural frequencies are. And so this tool basically lets you do it kind of right away. Okay. Okay, so the geometry that we're going to be doing this on is a gearbox. So this is a part that's very common in cars. In fact, all cars should have one of these. And so the reason I picked this part is that, the gearbox is part of a car, is part of an engine, and the engine is going to be vibrating. So, you want to make sure that every part that you design on your car, what the natural frequencies are, so that, it doesn't coincide with the RPM of the motor or the engine or anything like that. Okay. Okay. So let's go ahead and start this exactly like we usually do. So let's go ahead and open up ANSYS Workbench. So modal analysis is actually its own separate analysis. So you can see here. So if you look on the toolbox within ANSYS, you'll see that there is another analysis system called modal here. Okay. So we're actually not going to start there. So we're actually going to start with our good old tried and true static structural. Okay. So let's take static structural and kind of drag it into the workflow over here. And just like we usually do, let's go ahead and import our geometries. Let's right click on geometry, go to import, browse, and then let's go ahead and load in our gearbox that we just downloaded. Okay. Okay, so that gearbox it's a part that was developed within ANSYS, and so it should load without any issues, hopefully. And so after you load in that geometry, you should get a green check mark next to geometry. Okay, one other thing that we're going to do here is that we're going to load in another material. So we're going to test out two different materials and see how that affects the natural frequency. So just like we usually do, let's go ahead and double click on engineering data to bring up our materials menu here. Okay. So you can see by default, we have our usual material structural steel available to us. And then to that, we're also going to add a material called, let me see, we're going to add cast iron and see how that affects our results. Okay. And so let's go ahead and open up our engineering material library. So we're going to click on engineering data sources up here. We're going to go under general material. Okay. And it should be here. Yeah. So under general materials, you should see the material called gray cast iron. So let's go ahead and click the plus sign, and that's going to add that to your project. Okay. And so if we come back to our materials menu, you should have two materials loaded, one being structural steel and the other being gray cast iron that we just loaded. Okay. Okay. Any questions on this? Is everyone able to load in gray cast iron as one of the materials for the activity? Okay, good. Okay, so let's exit out of this. Let's go ahead and open up ANSYS Mechanical. So I'm going to go ahead and double click on model right here. Okay, so that's going to bring up our usual ANSYS Mechanical. Any second now, ANSYS. There you go. Loading, loading. Okay, there's our gearbox. Okay, good. All right, so let's go ahead. We can go ahead and rotate around. We can see that we have a nice assembly of parts here. Okay. And in fact, our gearbox is actually made up of three different parts. So we have one part for the base. So that's where it would probably attach to the car. We have one for the flange, and so that's all of these parts here. So that's where the rods are basically inserted into. And then we have another part for the housing. Okay. Okay. So one thing you'll notice here is that, this housing part is actually a shell model. And so it's actually only very, very thin. So if you look at under the geometry part of the model, you can see that the housing has a question mark next to it. Okay. And so what that question mark means is that, ANSYS wants us to specify some information on it before we move forward. Okay. And that piece of information that we need is we need to specify the thickness of that gearbox. Okay. And so if you look into the specifications on the document, you can see that the housing there has a thickness of 3 millimeters. Okay. So I'm going to go ahead and switch the units here to millimeters. Okay. I'm going to set this thickness here to be 3 millimeters. I'm going to hit 3 and then enter. Okay. And so that's going to specify the thickness of our housing. Okay. Okay. Another thing that we need to do is we need to set the connections. Okay. And so remember, whenever we have a shell part, shells are always, you almost always have to specify the connection manually for any shell or beam elements in your part. Okay. And so if you open up the connections tab within ANSYS Mechanical itself, you'll see that we only have one contact region. So the contact region is between the flange and the housing. Okay. But the housing itself is actually not connected to the base. And so we need to add one more connection group there. Okay. So just like we did in activity 4, I'm gonna right click on contacts here. We're going to insert. And so what we're going to insert is we're going to insert a manual connection region, okay, or a manual contact region, excuse me. Okay. And then we're going to bond together the housing and the base. Okay. Okay. So first thing is I'm going to click on the top surface of the base itself. And so that's going to be the target. Okay. And then for the housing is a shell. So the only way that we can click on this is we can click on all the edges on the bottom here. I'm going to click on each edge of the housing shell that's on the bottom, the one that's making contact with the base. Okay. So you should have 4 edges there. I'm going to specify that as the contact and then hit apply. Okay. Okay. Remember our rules for the contacts here. So, whenever you're contacting 2 bodies, it matters which one that you specify as the target and which one you specify as the contact. Okay. Whichever surface is the bigger one between the 2 that you're trying to contact, you want to specify that as a target. And so since our base is much bigger than each of the edges around the housing, we specify that one as the target. Okay. Okay. All right. Any questions on this so far? Okay, good. All right, so next thing we're going to do is we're going to mesh this geometry. So unlike our previous activities, we're not going to worry too much about the mesh. And so I'm going to right click on mesh right here. I'm going to go ahead and just generate the mesh. Okay. The nice thing about modal analysis is that, it's pretty robust. And so you don't actually need that kind of a mesh. Now, if you're going to use this geometry here to perform some other type of analysis, and so if you did want to do like stress analysis, you would probably pay more attention to the mesh. But for this case, since we're just doing a modal analysis, I'm just going to put a default mesh on the gearbox. Okay. Okay. So very, very simple mesh. Okay. Next thing we're going to specify here are the boundary conditions. So that's loads and constraints. Okay. So our constraints in this case is very simple. And so, this gearbox is going to be fixed at its base. And so first thing I'm going to do is I'm going to add a fixed support. Okay. So I'm going to right click on static structural A5, insert fixed support. And so I'm going to fix this bottom surface down here. Okay. So that's our fixed support. Technically, at this point, we are ready to run the modal analysis, but the modal analysis only really requires us to have some kind of fixed constraint. Okay. But just to kind of demonstrate, you know, the capabilities to add pre-stress, we're gonna add some loads onto this gearbox as well, okay? This is also a good opportunity because we're gonna use a different kind of load today, one that we've never actually used before, and that is a bearing, okay? So actually, let me bring back up the PDF here, and let me kind of scroll down, okay? Okay, so we're going to be applying loads onto each of the holes here that are on the outside of the gearbox, okay? So there are 4 holes on the outside here, and each one is going to have a bearing load, okay? So what is a bearing load that you may ask? So a bearing load is very similar to a force load. It's just that how that force is distributed along the surface is different, okay? So a bearing load is meant to represent a situation where you have some kind of cylindrical object that's going inside a cylindrical hole, and then that cylindrical rod is being pulled in a certain direction, okay? And so if you were to insert, you know, a rod into here, okay? And so let's say then you apply a load on the rod in this direction, okay? Then that force is going to be transmitted into the flange of the gearbox itself, but that force is not going to be evenly distributed across the entire inner surface, right? And so because we're dragging the rod this way, most of the force is going to be concentrated on kind of that surface that's contacting that rod, okay? Okay. And so in other words, you know, the bearing load will be distributed like the following. So in this case, you know, we're looking at a situation where we have a bearing load that's applied this way, okay? And so since this is a force that's basically, you know, determined based on contact, then all of that force is going to be distributed on that section of the cylinder that's in contact with the rod, okay? So it's basically an asymmetric distribution of the load itself, okay? Okay. So bearing loads are very useful. And so for your final project, if you have a situation where you have rods and you're basically applying loads on them, definitely consider applying a bearing load because it's, you know, it kind of distributes that load in a bit more of a realistic way. Okay. Okay. And so because we have 4 holes right here, you know, it helps to kind of label them. And so, you know, this is hole A, hole B, hole C, and hole D. Okay. And the loads that we're going to be applying on these holes are given by this table right here, okay? Okay, so let's go ahead and input these loads. Okay, so I'm gonna first apply the bearing load on a hole A. So to apply a bearing load, you're gonna right click on static structural A5. You're gonna come right here, and so you'll see that there's a button here to insert a bearing load, okay? So let's go ahead and click on that. First thing we're going to do is we're going to apply it onto a cylindrical surface, which is this one right here, okay? Okay, so that is hole A. So if you go back up to the diagram here, that's that one, okay? And we're given the X, Y, Z components of the force, you know, for that hole, okay? Okay, so let's go ahead and apply these force components into ANSYS itself. So, just like we usually do when we define our force, we're going to do it by components. And so we're going to switch this define by to components. Okay. So that's going to allow us to specify the X, Y, Z components of that force itself. Okay. All right. And so the loads in this case, if you go back to the table, on hole A, we have a force of 16,000 newtons in the X direction, a force of 30,000 newtons in the Y direction, and a force of 16,000 newtons in the Z direction, okay? So let's go ahead and import all those in. So X direction, we have 16,000 newtons. Y direction, we have 30,000 newtons, okay? And in the Z direction, we have 16,000 newtons, just like that, okay? Okay. So before we apply the other loads, I'm going to show you something, okay? Oops. So let me go ahead and specify some output fields here. So I'm going to go ahead and insert a total deformation. Let's go ahead and see the equivalent stress as well. Okay. So I'm going to hit solve. Okay. And you're going to see that we obtained an error. Okay. Okay, so if I double click on this error, this error is telling us that our bearing load has a component in the axial direction, okay? So it says this is not allowed. So if an axial component is desired, then we need to create a separate force for that component, okay? So what does that mean? So let me bring up our bearing load again here, okay? Let me kind of rotate this figure here. Okay. So what ANSYS is complaining about here is that our bearing load has what's called an axial component. And so axial component means that there is a component of the force that's going right down the barrel of the cylinder. Okay. So that's not allowed for bearing loads. So a bearing load is strictly a load that's being impinging upon. It's an impingement load on the cylindrical shell around the rod. Okay. If we have a force in the axial direction here, that would be considered a frictional force, right? And so the only way we can get a force kind of in this direction is that if there's some friction between the rod and the hole that it's being inserted in, okay? So we can't actually do that for a bearing load. Okay, so the way to fix this is that for our bearing load here, we can see that the axial direction is in the z direction right here. So we need to delete our z component here, okay? So we're going to make our z component 0 for this bearing load. So then now we only have a force in the x and y direction, okay? But to apply that load in the z direction, we need to create another force that's being applied on that surface, okay? And we're going to apply that just as a normal force, boundary condition. Okay. So once again, I'm going to hit apply. I'm going to apply it on the same hole A. We're going to define this by components. Okay. And then we're going to input our Z component of that force, which was 16,000 newtons. Okay. And just because we have a lot of forces here, I'm going to go ahead and change the names of these loads. Okay. We'll call this bearing load A. And then we'll call this force here axial load A. Okay. And so because that hole A there has axial components, we have to kind of split that up into two separate loads. We have a bearing load for the X and Y component, and then we have a regular force load for the Z component. Okay. All right. Any questions on that about why we do that? Okay. Okay. So let's go ahead and apply all the other modes on this model. Okay. So we have a load on hole B, load on hole C, and a hole D. Okay. So I'm just going to go ahead and do those really quickly here. Okay. So hole B, let's see, hole B, we have 6,000 in the X direction and 30,000 in the Y direction. So we have no component in the Z direction in this case, and so, we don't have to worry about any axial forces here, okay? Okay, then let's go ahead, let's rename this. So this is bearing load B. Okay, next we have the force on hole C being that one there. And so we have 30,000 in the X direction and minus 3,000 in the X direction, minus 30,000 in the Y direction. There, components. Okay. 3,000 and then minus 30,000. Okay, good. And then finally, we have the forces on a hole C, or hole D, excuse me. Okay. So we can insert a bearing load, apply it on this surface here. Okay. We're going to do this by components. Okay. So for hole D here, we have an axial component again. So we need to apply that as a separate force. But we can go ahead and apply the forces in the X and Y directions. We have minus 25,000 and then a minus 30,000. And this is bearing load D. All right, and then we're going to add one more load here. So we're going to add a regular force load. applied on this surface here. And this has a magnitude of minus 16,000 in the z direction. This right here is axial load. Okay. So you should have 6 loads in total. So 4 bearing loads, 1 for each of the holes, 1 axial load for hole number A, and then 1 axial load for hole D. Okay. And of course you have your fixed support as well. All right, any questions on that? Okay, good. All right, so let's run our simulation just to make sure all of our loads are consistent. It should be. Okay. Okay. So you can see here we have our deformation plot that looks like the following. Okay. It's a little bit different than what I have in the notes. Let me just double check everything, make sure I said everything correctly. That's newtons, there will be. Okay, whatever. Okay. So we should get a figure that looks like the following. Okay. All right, any questions on the static analysis? Yeah. We're supposed to delete just the z component of the bearing. Yeah. Yeah, because for the bearing load, you can't have any axial components of the bearing load, so we make that 0. But everything else should be okay. Just double checking one more time, just to make sure I got it all correct. Okay. All right, so that's the static analysis, and so that's the only thing new here was just the bearing load. But that's not the point of this activity. So the point of this activity is to do the modal analysis. Let's go ahead and do that. And so to do modal analysis, we're going to go ahead and close ANSYS Mechanical for now. Okay. Don't close Workbench, and so Workbench is we're going to use it in a second. Okay. But we're going to do something that we've never done before in this class, is we're going to link 2 analyses together. Okay. All right. So the tool that we're going to use here is called modal. Okay. So what you're going to do is you're going to click on modal and then drag it up to our geometry here. Okay. So you're going to click and drag modal, and you're going to drag it onto model of your static structural. Okay. And so what that's going to do is that it's going to link these 2 analyses together, so it can use the same mesh and the same boundary conditions and the same material properties as well. Okay. Okay, so I'm gonna go ahead and drop that in. Okay, so once you have that, let's go ahead and double click on setup here. And what that's going to do is going to reopen mechanical, but now we're going to have all the modal tools available to us. Okay. Okay. So once you've kind of set your modal, you've attached modal to your static structural analysis, and you reopen the part, and you should see your geometry again. Question? So you click and you drag it onto static structural. And so you come back to ANSYS Workbench, you click on modal, and then you drag it directly onto static structural like that. Yeah, so the idea is to have the modal kind of linked directly to your static structure. So you should have these 3 connections. Yeah. Make sure you close mechanical before that. So close mechanical, drag and drop modal, and then reopen mechanical after. Yeah. Okay. So you can see here that, this looks very similar to our, to our analysis from before, except the only difference now is that we have modal analysis available to us on the bottom. Okay. Okay. All right. So this part's really important. So remember, when you're doing modal analysis, you can either include pre-stresses into your model. And so pre-stresses basically means any kind of internal forces or internal loads that's applied, that developed because you applied loading to the model. Okay. And so if you wanted to do that, you can come down here to modal B5 and then change the pre-stress environment to static structural. Okay. So what that's going to do is that it's going to load in all the boundary conditions and all the loads from your static structural analysis and then apply those onto your model. Okay. So we'll do that in a second. But first thing we're going to do is I'm going to show you, you can actually run a modal analysis without applying any loads at all. Okay. Okay. But if we're not using the boundary conditions from our static structural, then we do need to apply our fixed support. Okay. And so before we rerun this, let's go ahead and right click on, let's right click on modal B5, and then you're going to click on fixed support Q. Okay. You're going to click on fixed support, apply it onto the bottom surface here. Okay. All right. All right, and so all we have to do here is we just have to hit solve. Okay, it's that easy. So all you have to do, you only need a mesh and you only need a fixed support, and you can run modal analysis from there. Okay, and you can see it's very, very fast. Okay. Okay, so after you run your modal analysis, you should be able to view your solution. Okay, and so you want to view the solution under modal, so it's going to be solution B6. Okay. And after clicking this, you should see that the area on the bottom of the screen is going to update to show you all of the natural frequencies. Okay. Okay. So for this model right here, you can see that we have one natural frequency at 350.88 hertz. Okay. Another natural frequency, the second harmonic is 627.39 hertz. Okay. Third harmonic here is 652. Fourth one is 691, 722, and 898. Okay. Okay, so was everyone able to get the list of natural frequencies for the gearbox? Okay. Good. All right, and so that's basically it. So that's modal analysis for you. So the whole part of the bearing loads was just to kind of pad out this activity to make it seem longer than actually. But modal analysis, like I said, very, very simple. Okay. Now, one interesting thing that you can do, right? So, probably the most important thing that you're obtaining from modal analysis is you want to obtain the natural frequencies. But it could also be useful to view, what the resonant modes actually look like. Okay. Okay. So to view the resonant modes, you can go ahead and highlight all of the natural frequencies here. So you don't have to do all of them, but I'm just selecting all of them just for you so you can see. Okay. So go ahead and select, I'm going to go ahead and select all of them. You're going to right click, and then you're going to click on the button for create mode shape results. Okay. Okay. And so doing so, you can see here that we have 6 new deformation plots that appeared under solution B6. Okay. So I'm going to go ahead and solve it one more time just to evaluate them. Okay. And now you can actually see the modal results. Okay. So remember, what the modal results show you is that if a resonance were to occur in your gearbox, this is what the deformation would look like. Okay. And so let's look at the first resonant mode. And so this is the first resonant mode that corresponds to the frequency of 350.88. Okay. And in fact, you can play the animation to kind of see what it would look like as well. And so to play the animation, you can use this kind of animation toolbar up here. And so you can see that when you have resonance that occurs with 350.88, the entire structure looks like it's kind of rotating this way. Okay. Okay. And so you can do the same thing for all the other resonant modes as well. Okay. Some of them are actually really interesting. So you can see here that, you know, for some of the resonant modes, it's actually the whole gearbox is kind of expanding apart. Okay. Okay, so you can view kind of what the modes look like for all 6 of these, right? But remember, you want to be careful with viewing these modes, right? Remember what we talked about on Tuesday. So when you're viewing these modes, you know, the way ANSYS displays it to you is that it shows you the modes as a total deformation, right? It even has units. And so you can see here that the unit of this total deformation is in millimeters, okay? But remember, you know, we haven't actually applied any loads on this gearbox yet. And so these deformations, they're not true deformations. Okay. So don't take these numbers at face value. So, you know, don't take these numbers as, you know, if you were to apply resonance to this model, you know, you're not going to get a deformation of 10.917 millimeters. Okay. Because that depends on the magnitude of the loading, just like we talked about on Tuesday. Okay. These numbers here only exist so that you can see kind of the relative changes or which areas are going to deform more. Okay. But the true deformation, you're not going to obtain the true deformation unless you actually apply an oscillatory mode, which we're not doing in this case. Okay. Okay. Any questions on this? Okay. So the last thing I'm going to show you, you know, before I stop talking, is you know, what happens if you change the pre-stress here. Okay. So, you know, we went through the whole trouble of running a static structural simulation, right? And so by running a static structural simulation, we had internal stresses develop within the part itself, right? So those internal stresses are going to affect your resonant frequencies, just like we talked about on Tuesday, right? So if you remember, we talked about on Tuesday, we talked about the string within tension, okay? And so one of the factors that change the natural frequency in that string is the amount of tension within the string itself, okay? So the same thing is true for these mechanical parts. And so the internal stresses are going to change the natural frequencies within this part itself, okay? So to view that, you know, you're going to go up to pre-stress right here under model B5, and you're going to switch it from none, and you're going to switch it to static structural, which is basically the static structural simulation that we did earlier, okay? Okay, so now this is applying all the loads and constraints from the static structural, okay? Before you solve it again, you know, you're going to see here that your fixed support is actually redundant, okay? Remember, so this second fixed support, this is one that we had when we weren't applying any loads. But since we're inheriting all the boundary conditions from static structural, now the fixed support from the static structural is being applied for us, okay? So I'm just going to go ahead and suppress this just because we don't need it, okay? And then I'm going to rerun the modal analysis. And so we're going to see how big of an impact the boundary conditions make. So, you know, take a mental note of these frequencies. Actually, I'll do one better. I'm going to take a screenshot. Okay. Usually there's something that appears over here. Okay. Let me open up a Word document. This is just to kind of show you the change in between the frequencies. Okay. Okay, so now we've changed the pre-stress to static structural. Let's rerun the simulation and let's see how the resonant frequencies change when we add in those internal stresses. So actually right now, ANSYS is actually running 2 simulations. So first it's running its static structural simulation, and then it's running the modal analysis on top of that, okay? Okay, so let's see how much these change. So this is the screenshot of the modal frequencies when we didn't apply any modes, and let's see how they change when we do apply the modes, okay? So our first resonant frequency, after we applied the mode, changed from 350.88 to 350.93. So you can see there is a massive change there between the natural frequencies, which of course I'm being sarcastic. So, you know, so a lot of times, you know, the internal stresses, you know, don't make that big of an impact on the you know, on the natural frequencies. And so if you're interested in a modal analysis, you can just run it just by itself. That's totally fine. You know, but it does make a little bit of a bigger change kind of near the tail end on some of the higher frequencies. But, you know, a lot of times, you know, we don't really worry about the higher frequencies all too much. Okay. All right. Any questions on that? Yeah.
What did you?
Yeah. So I changed the pre-stress condition. So under modal B5, you can see here that there's a condition for pre-stress. So originally we had it as none. And so when we have no pre-stress there, that means, you know, we're not applying any loads. And so what I did instead was that for the pre-stress environment, I changed that to static structural. And so what that does is that it imports all the loads and all the constraints from the static structural simulation and incorporates that in as a pre-stress for this move. Yeah. Okay. All right. Any other questions on this modal analysis? Okay. All right. So if you're interested in kind of experimenting with a modal analysis a bit more, if you look at the PDF, you'll see that there are a few kind of extra activities here. And so, you know, you can change the material properties. And so we did this entire analysis with structural steel. You can see how the numbers change when you change the material to gray cast iron. Okay. So you can see the effect of the material properties on the modal frequencies. Okay. You can change the geometry, so you can try you know, adding thickness to the model and seeing how that changes the natural frequencies. Okay. So these ones are good to do just to kind of build your intuition in terms of, you know, what factors will affect the natural frequencies. Okay. Problem five is kind of a fun one. And so problem 5 kind of goes back to some of the activities we did earlier in the class, where, you know, I'm having you use the simulation to target a specific design. Okay. And so with problem 5, I want you to make changes to either the materials or the geometry to get a natural frequency of around 300 hertz. Okay. Excuse me, I want you to change it to be around 200 hertz. Okay. So you can make changes to the thickness, you can make changes to materials in order to get this part here. Okay. Problem 6, don't worry about, you know, because you're not turning anything in. But if you're interested in learning more about modal analysis, I would definitely recommend doing problems 3, 4, and 5. So if you're following along with the document, we did up to problem 2. Okay. And I just realized that the numbers that you're going to see in your the numbers that you saw kind of here are probably different than the ones in the PDF. That's because in the PDF I changed the material to gray cast iron, but everything we did in the class just now was with structural steel. Okay. Any questions on anything before I we just kind of start office hours? Okay. All right. So for the rest of class today, you guys are free to continue working on activity 6. Remember, you're not turning anything in for it. And so, you know, only if you want to use it for your final project, I would recommend doing more. But for the rest of class today, you know, if you are working on your final project and you have questions for me, you want me to look at something, if you're running into an issue or you're not sure about, you know, a particular loading scenario or how you're setting up the whole thing, you know, I'm available here for questions. So I'll be here until 6:45. And so if you want to talk to me, go ahead and raise your hand. If you are on Zoom and you want me to look at something, just drop something in the chat and I'll come by and talk to you. Okay. But if you guys are taking off, you know, I just want to say thank you guys. You know, this is not everyone in the class. I realize that, but you know, next week, I know people are going to be in and out of the class just because there's no formal lecture. So I just want to say thank you guys for a great semester. You know, I think, you know, a lot of you kind of know this, but you know, I'm not exactly feeling great about this job right now. You know, really crappy provost. My dean hates me, and you know, honestly I don't know if I'm gonna be working here long term, but I am really happy that I was able to teach you guys. You guys are all great. You know, I was just talking to someone earlier in office hours that, you know, compared to where I was at the beginning of the semester, compared to how I'm feeling now, I feel much better about this job because you guys are such great students. So thank you guys for being a great class. I really enjoyed being a professor, and you know, hope to see you guys next semester. Thanks, guys.
Thank you.
Oh, if you haven't picked up your exams, I have them up here too. I'll come back next semester. We'll see. Yeah, I mean, I'll come see you guys around. I mean, I always get really passionate to see people all the places. I want to see you. You guys, thank you for that.
Are you teaching any of this next semester?
I want to, I'm not sure which one is going to be good, so. So I know they posted, the department posted 4 more electives, I think on Monday of this week. I know we're trying to add maybe at least 2 or 3 more electives, and so if I am going to teach an elective, it's going to be but it's either going to be, I requested 442, which is cardiovascular class, or 417, which is computational. Yeah, so just keep an eye out, once I get the news, I'll let you know. Yeah, you need to source. Just put it in the web. So if you download it from my online website. Okay.
So you said there's no formal lectures next week?
No, so it's all just going to be this. Actually, yeah, so I'll be here and then we'll work through the project, have some questions.
Yeah, thank you.
Yeah.
idea.
Yeah. Yeah.
So, from speaking, from you from the handle that I do, I know like a bit about it, but I'm sure to, I have this one that I about.
Yeah.
So, going on to the other project, if I do something that's like that, I want to make it, more complex,
It's not necessarily making it complex, it's just kind of having a clear objective. of What it comes to accomplish with these information. So a lot of times these are design questions. And so for a water bottle, you could ask a question, try different materials. So which one is better? But then, different materials in there have different costs. So you can say, cost per strength or something like that, but that's.
am I about to like, so the reason why I wanted to use this type of about this stuff is regular plastic bottle, but just just made out of plastic.
Yeah.
When you put something that's made out of steel and like foams that are attachable to it, right, or replaceable, it adds different cost to it.
Yeah.
And it adds also different stress and response to properties to it.
Yeah.
Right.
Yeah.
So I want to talk about like water bottle components. At the same rate, all the components of a line for one.
Well, I mean, if you can find an assembly that has all of them, that'll probably. Then you just simulate just that assembly, you can look at the stresses and deformations of each part.
So individually break them all down into like the different stresses that we experience.
Yeah. So that's definitely one way you can say, from that situation, you can say, which of these components are the most likely to fit. Probably depending on how you know them, a lot of different components, whether it's one from a large height, whether it's being crushed or something like that, you probably have different skills.
It just depends on the situation that I put them in.
Exactly.
Such as like, is one of them, be run over by the car.
Exactly.
The following.
Yeah. You can look at situations where the water bottle is full, maybe that's going to have more impact when you drop it. If it's not full.
I can do multiple ones to throw on report, right?
Sure.
So identify multiple scenarios or like the resistance.
Yeah.
So it's not just like limited to like a few things, right?
No, yeah. I mean, the whole idea of the final project is let your kind of creativity kind of run the plot. And you have all the tools, so you know ANSYS pretty well. And so now it's just how do you use ANSYS? The final project is more about not just using ANSYS, but how do you use ANSYS to answer important design questions or analysis questions. And so, what I want to see, what I'm going to be looking at a lot of the final project, you have like a clear objective, a clear kind of motivation for why you're simulating this, and does your simulation result actually correlate with what you're trying to for the question?
Also, I work from let's say from your customer's point of view, right? You want to invest into something that is durable for last a long time.
Yeah.
Right. And that's working on. This is why this according to NPA with investment.
Yeah.
So just go on develop the paper to talk about why all these things and show that it's good.
Yes. Perfect. Yeah. I think that's a great idea.
Thank you.
Yeah. Ah, okay. Yeah. So one interesting angle that I don't think anyone's done in the past is because I'm thinking about how easy would it be to obtain a CAD model for a particular part. So one interesting angle that you can take is you can take like a historical kind of structure. Um, I say historical, maybe like maybe landmark probably better name for it. Like you can take like the Golden Gate Bridge, for example. Maybe not the whole bridge, but just a component of the bridge. Because people have probably catted that up, or maybe just even just a general suspension bridge. And then you can do simulations on that. So you can probably find a CAD model for that and load that up into ANSYS, apply forces onto it, and use that to kind of maybe answer some questions and why the Golden Gate Bridge was designed in this way. Yep. Yeah. So one thing that I did when I was in grad school, I did analysis of a section of the Eiffel Tower. So Eiffel Tower structure is very, very interesting. So you can take a section of that Eiffel Tower and do analysis on that. Yeah. Mhm. Yep. Yeah. So I'll be here next Tuesday and Thursday. I don't have any lectures planned, but they're just gonna be just open office hours just like this. And so I'll just be kind of sitting around, and if you want to come in, work on your project and ask me questions or anything like that, have me look at stuff, then you can do that during lectures next Tuesday and Thursday. I'll have my regular office hours next week too.